So, picture this. Professor Moriarty is standing somewhere inside the Louvre in Paris, and he's wearing this disguise that is just flawless. I mean, so meticulously crafted that no detective on Earth could ever recognize his face.
Right, you could literally bump into him and stare him right in the eyes, and you'd have, no idea you're looking at the criminal mastermind of the century.
Exactly. But the thing is, Sherlock Holmes doesn't even care about his face, because Holmes knows this secret, that Moriarty's colossal ego has basically painted a giant mathematical bullseye on the floor right beneath his feet.
It is such a phenomenal setup. And well, welcome to you, our listener, joining us today for this custom-tailored deep dive into an incredible scenario. It's a situation where classical detective work just completely hits a brick wall and rigorous mathematical optimization has to take over.
Yeah.
Our sources today are this brilliant combination. We have a playful, high-stakes narrative puzzle involving Holmes and Moriarty, and is paired with a really deeply accurate breakdown of real-world calculus and geometry.
And the mission of our deep dive today is to unpack that exact mathematical approach. We're going to figure out how to calculate the absolute best viewing angle and, the optimal distance from a wall to view a masterpiece.
Because if we can find that perfect spot, we catch the invisible man.
Right. And the stakes here completely change the nature of the pursuit. Dr. Watson is panicking, looking at this massive, shifting crowd of tourists in the museum, and he's just wondering how they could possibly spot a master of disguise.
But Holmes, he really understands the psychology of his enemy. I mean, Moriarty considers himself superior in literally every way.
Oh.
So if he travels to Paris to view the Mona Lisa, he will not settle for, a slightly off-center view.
No way.
Or an angle distorted by glare. He will absolutely demand the mathematically perfect vantage point.
Which completely changes Holmes' strategy. He's no longer looking for a guy in a trench coat. He's looking for the one guy in the room who accidentally turned himself into the center of a geometry puzzle.
Yeah, that's a great way to put it.
It's exactly like trying to find the best seat in a movie theater, right?
Mm-hmm.
Something we've all experienced. If you walk into a theater and you sit way too close to the screen, you're craning your neck and your peripheral vision is just totally overwhelmed.
Oh, yeah. You can't even take the whole image in. Your eyes are constantly darting around to compensate for that extreme angle, which causes visual fatigue.
But then if you get frustrated and move all the way to the back row, the screen suddenly feels like a postage stamp. I mean, it occupies such a small percentage of your visual field that you lose all the immersive detail.
Right.
So between those two extremes, there is this Goldilocks zone, a specific row where the screen perfectly fills your vision without causing any strain. And we need to find Moriarty's Goldilocks zone for the Mona Lisa.
To do that, we have to stop thinking like detectives and, start thinking like architects or geometers.
Mm-hmm.
We need to build a mental map of the visual space in that room.
Mm-hmm.
So I really want you to mentally draw this scene with us. Picture the wall of the Louvre. The Mona Lisa is hanging there. The bottom edge of the painting is at a specific height off the museum floor. And we'll just call that height A.
Got it. The bottom of the frame is A.
And the top edge of the painting is higher up on the wall, obviously at height B. Now, Moriarty is standing somewhere in that room. His eyes are at a specific height off the ground based on how tall he is, which we'll call H.
Right.
And he's scanning this mysterious unknown distance away from the wall. This horizontal distance straight from his eyes to the wall is our critical variable. We'll call it X.
So X is our missing puzzle piece. It's the actual physical spot on the floor we need to identify to catch him.
Exactly. And finding it relies entirely on understanding how Moriarty experiences the painting. When he looks at the canvas, the top edge and the bottom edge project an angle back to his eye.
Right.
This is his viewing angle. We'll call it theta. And the core objective of this entire puzzle, and frankly Moriarty's absolute uncompromising demand, is to maximize that angle theta. The larger the angle, the more of his vision is dominated by the masterpiece.
Okay, let's unpack this. Because if I'm Watson, I'm standing in the Louvre thinking, why are we making this so complicated? If the whole goal is simply to maximize this viewing angle, theta, why can't we just measure theta directly? Why do we need to build some complex mathematical formula just to figure out how a guy looks at a flat wall?
Well, the difficulty comes from the physical reality of space. Theta isn't attached to anything solid. It is essentially this floating angle hovering in the middle of the room, wedged right between the line of sight looking up at the top frame and the line of sight looking down at the bottom frame.
It doesn't connect to the floor or anything?
No, it doesn't connect to the floor and it doesn't connect to the wall at a neat, measurable right angle. which makes it incredibly difficult to calculate directly based on our physical distances, like height and distance from the wall.
Yeah.
We have to anchor it to something solid.
Oh, I see.
We do this by imagining a perfectly horizontal line shooting straight for Moriarty's eyes, directly to the wall. This horizontal line hits the wall at a 90-degree angle, giving us right-angle triangles. And in geometry, right-angle triangles are basically the key to unlocking almost any spatial relationship.
Because once you have a right angle, you can start applying rules that are absolute.
Precisely. So from that horizontal eye-level line, we measure the angle looking up to the top of the painting. Let's call that upward angle alpha.
Okay.
Then we measure the angle looking from that same horizontal line down to the bottom of the painting. We'll call that beta.
So alpha is the big angle pointing to the top, and beta is the smaller angle pointing to the bottom. And since theta is just the viewing area of the painting itself, it's simply the difference between those two measurements, right?
Exactly right.
Theta equals alpha minus beta.
That gives us our conceptual anchor. But we still need to connect those floating angles to the actual physical measurements of the room, the height of the painting and the distance x. This is where we shift from pure geometry into trigonometry.
Here we go.
Specifically, we're using the tangent function.
Tangent is all about the relationship between the sides of a right triangle, right? Like how far you're looking up compared to how far back you're standing.
That is the perfect way to visualize it. The tangent of an angle is the opposite side divided by the adjacent side. So for the angle looking at the top of the painting alpha, the opposite side is simply the vertical distance from Moriarty's eye level up to the top frame.
Which would be height b minus his eye height h.
Exactly. And the adjacent side is just his distance from the wall, x. So the tangent of alpha is that vertical difference divided by his distance back.
Makes sense.
The same logic applies to the bottom of the painting. The tangent of beta is the vertical distance from his eye level to the bottom frame, so height. A minus height h divided by that same distance x.
But we don't care about alpha or beta on their own. We only care about theta, which is alpha minus beta, which means we have to combine these expressions using one of those giant trigonometric identities from high school, don't we?
Unfortunately, yes. We use the identity for the tangent of a subtracted angle. And when you take our physical distances and plug them into that identity, you end up with a massive, unwieldy fraction.
Yeah, I'm looking at our source notes here, and it is a beast of an equation. On the top of the fraction, you have your variable distance x fighting against the total height of the painting.
Yes.
But on the bottom of the fraction, you have the distance squared, plus this incredibly messy combination of how tall the man is versus both the top and bottom of the frame. I mean, it's this massive tug of war between the distance he stands and the heights involved.
It looks completely intimidating.
Yeah.
I mean, most people see an equation like that and just assume the problem is hopelessly complicated. But what's fascinating here is a beautiful mathematical truth about the tangent function itself.
Yeah. What's that?
Well, remember, Moriarty wants to maximize the viewing angle, theta. If you look at the derivative of tangent theta, it is a squared function.
Meaning it's always a positive number.
Always positive. Which tells us that between 0 and 90 degrees, which, is the only realistic physical realm for someone looking at a wall, the tangent function is strictly increasing.
Oh, wow.
Yeah, as the angle physically gets wider, the tangent value gets larger.
Oh, that is a brilliant shortcut. So we don't actually have to isolate and solve for the raw angle theta directly, which would be an absolute nightmare of inverse functions.
Exactly.
Maximizing this messy tangent equation will automatically give us the exact same spot on the floor that maximizes the angle itself. They just rise and fall in perfect lockstep.
It reflects the physical reality of the space beautifully, and honestly, it saves us an enormous amount of calculation.
But, I mean, even with that shortcut, we still have that massive tug-of-war fraction to maximize. And anytime you want to find the absolute peak maximum of an equation, you need calculus. You have to find the derivative of that equation to find where the slope hits zero.
That's right.
But taking the derivative of a massive fraction with our variable x sitting in both the numerator and the denominator, isn't there a rule for that?
There is. It requires using the quotient rule. And applying the quotient rule to an equation this dense is just a recipe for a massive, tangled headache of algebra.
I can imagine.
I mean, it is entirely possible to do, but it is incredibly tedious, it's prone to human error, and frankly, it just lacks elegance.
And Holmes and Moriarty, for that matter, are all about elegance. Which brings us to one of my absolute favorite tricks from our source material today. Instead of fighting through the quotient rule to maximize this massive fraction, the mathematical approach changes the rules of the game.
It really does.
It flips the script, literally. We are going to minimize the reciprocal.
We turn the equation completely upside down.
I want to frame this visually for you listening because it is such a clever shift in perspective. Imagine you're looking at a 3D topographical map of mountain range, right? And you're tasked with finding the exact GPS coordinates of the absolute highest, most jagged peak.
Which is very difficult.
Exactly. Mapping the math of that towering peak is incredibly complex. But if you take that physical map and flip it completely upside down, that towering peak instantly becomes a smooth, deep valley.
And finding the bottom of a valley is a much simpler physical process.
Right. You just drop a marble, and gravity rolls it right to the lowest point. The math to find the bottom of that valley is vastly easier, but it gets you the exact same GPS coordinates on your map. So instead of maximizing tangent theta, we flip the fraction and look for the minimum of 1 over tangent theta.
That analogy perfectly captures why mathematicians do this. By flipping the fraction, the distance squared and the messy height combinations move to the top, and the simple variable x moves to the bottom.
Oh, that's smart.
This allows us to split the fraction apart, isolating our variable x from all the constant heights in the room.
Because the height of the painting and the height of the man aren't changing while he walks around. Those are just fixed numbers in reality.
Exactly. Only his distance, x, is actively changing. So to clear out the visual clutter of the math, we can gather up all those fixed constant numbers and substitute them.
Okay.
We take the constants from the first part of our split fraction and just call them p. Then we take the messy constants from the second part and bundle them all together into a placeholder called q.
That is so satisfying. You take this terrifying multi-tiered fraction, and by just sweeping the constants into these neat little boxes called p and q, the nightmare instantly shrinks down to a beautiful, simple expression. P times x plus q divided by x.
Px plus q over x. We transformed a complex quotient rule problem into a straightforward two-term expression. And remember, because we flipped the topographical map upside down, our goal is simply to find the minimum value of this new equation.
Finding the bottom of the valley.
Exactly. To find the minimum, we take the derivative of px plus q over x with respect to our distance, x. The derivative of px is just p. The derivative of q over x is negative q over x squared. So our derivative is simply p minus q over x squared. We set this equal to 0 to find the lowest point.
Which means p must equal q over x squared. And if you move the variables around, multiply by the distance squared, divide by p, you are left with x squared equals q divided by p.
And taking the square root gives us our final answer. The optimal distance, x, is the square root of q divided by p.
Here's where it gets really interesting. Because looking at the square root of q over p feels a bit abstract. It doesn't look like a room in the Louvre,
No, it doesn't.
But remember, p and q were just cardboard boxes we used to temporarily hold all those messy physical heights. If we unpack those boxes and plug the original painting and eye-level variables back into our final answer, something almost magical happens to the geometry.
The algebra collapses in on itself beautifully. Both the p box and the q box share the exact same denominator relating to the height of the painting. When you divide q by p, those terms completely cancel each other out. They just vanish.
All the complex trigonometry, all the floating angles, all the massive fractions we worried about earlier, they just melt away. The optimal distance, x, simplifies down to just the square root of the top vertical distance multiplied by the bottom vertical distance.
Right.
Specifically, the square root of b minus h times a minus h.
It proves that the perfect viewing distance relies entirely on the geometry of the painting relative to the specific observer's eye level. Nothing else in the room actually matters.
All right, let's catch our criminal mastermind. Let's take this elegant formula and apply the real-world numbers from our source intel. We are in the Louvre. The target is the Mona Lisa. Let's say the bottom edge of the painting's frame. Our height A is 8 feet off the ground.
The standard gallery height.
And the top edge of the painting height B is 20 feet off the ground. It's a massive installation for this scenario. And Professor Moriarty, standing somewhere in that crowd in his flawless disguise, has an eye height, our variable h, of exactly 6 feet.
Okay, so we have our constraints. Top is 20, bottom is 8, eye level is 6.
Let's work this out. Our formula is the square root of the top difference times the bottom difference. So the top of the painting is 20, minus his eye level of 6. That gives us 14 feet.
That is the vertical distance from his eyes to the top frame.
And for the bottom difference, the bottom of the frame is 8, minus his eye level of 6. That leaves us with 2 feet. So we have 13 and 2, We multiply those together. 14 times 2 is 28. So we're just looking for the square root of 28, which is, what, a little over 5?
It is exactly 5.3 feet.
Wow. That is his absolute mathematical destiny in that room. I mean, to get the maximum possible viewing angle of the Mona Lisa with those specific heights, Moriarty literally cannot stand anywhere else. He must stand exactly 5.3 feet away from the wall.
That 5.3-foot mark is his geometric Goldilocks zone. If the crowd pushes him forward to 4 feet, his viewing angle actively shrinks. If he steps back to 7 feet to avoid the crowd, the angle shrinks again. 5.3 feet is the absolute peak of the mountain.
Incredible.
He will wait however long it takes for that specific spot on the floor to open up.
I am so curious about the physical reality of this. Like, if he is standing exactly 5.3 feet away from a painting that stretches from 8 feet to 20 feet up the wall, what is his actual field of vision? What does that angle look like?
Well, if we take that optimal 5.3-foot distance and plug it back into our original tangent equation, we find that his maximum viewing angle, theta, is exactly 48.6 degrees.
48.6 degrees of pure vertical vision?
Almost 50 degrees of your central visual field is a massive amount of visual real estate.
Yeah.
I mean, the human eye's sharpest focal point, the fovea, only covers a few degrees. To have nearly 50 degrees filled by a single object means the painting is completely dominating his field of view.
Which means Sherlock Holmes doesn't need to look at a single face in that museum. He doesn't need to try and peer through impenetrable disguises or interrogate tourists.
Not at all.
He just needs to walk into the room, locate the exact center of the Mona Lisa, pull out a tape measure, walk exactly 5.3 feet straight back into the crowd, and slap the handcuffs on whoever is standing right there.
It is the ultimate trap, built entirely out of logic and calculus. Moriarty's own obsession with achieving absolute perfection dictates his physical location in space. He has mathematically cornered himself.
So what does this all mean? For you listening, I think it's a brilliant reminder that calculus, geometry, trigonometry, these aren't just abstract concepts designed to torture us on chalkboards.
Right.
They are literal foundational maps for how we optimize our experience in the physical world. Whether it's an architect calculating the slope of stadium seating, a museum curator deciding where to place a barrier, or a detective hunting a mastermind, these formulas allow us to parse through incredible noise to find objective truth.
If we connect this to the bigger picture, it really highlights the extraordinary power of synthesis. If you approach finding a perfectly disguised man as a purely qualitative detective problem, it is impossible. You will fail.
Yep.
But by synthesizing criminology with geometry and calculus, Holmes changes the entire nature of the problem. He turns an unsolvable qualitative mystery into an elementary quantitative calculation. Changing your framework often provides the solution your current tools cannot.
It is a stunning victory for logic. But looking at the physical reality of how this played out, it also leaves me with a final thought for you to ponder based on these findings.
Well,
think about Moriarty standing on that spot. He is 5.3 feet away. The painting is taking up a massive 48.6 degree vertical viewing angle. His vision is totally flooded by the canvas.
his peripheral vision is effectively neutralized by his focus on the massive subject in front of him.
Exactly. His field of vision is incredibly compromised. He is so focused on the math, so utterly obsessed with achieving the absolute perfect view that he has created massive tunnel vision.
That's such a great point.
It makes you wonder, does demanding the mathematically perfect view actually create the ultimate blind spot? I mean, does optimizing for this one single metric completely blind him to his surroundings, allowing Sherlock Holmes to casually walk right up beside him, totally unnoticed, until the trap is sprung?
A phenomenal question.
In our own lives, when we optimize relentlessly for one single perfect metric at work, in our routines and our goals, what are we becoming completely blind to right next to us?
And that is a powerful warning about the hidden costs of optimization.
Thanks for joining us on this custom-tailored journey, translating physical reality into geometry, finding the bottom of the valley, and catching a mastermind along the way. We'll catch you on the next deep dive.